Metals crystallize in different varieties of the cubic form of the unit cell. And in this case, metallic silver crystallizes in a face-centered cubic structure. In order to solve this problem, we need to visualize the face-centered cubic structure. Let's draw a diagram of it. We don't need very much. We really only need to look at one face. A face-centered structure has an atom at the center of the face. And then it has touching atoms at the corners. This is a representation of the face-centered cubic structure of silver. Now, how many silver atoms does a unit cell contain? Each of the corner atoms is 1/8 within the unit cell, and each of the face-centered atoms is 1/2 within the unit cell. So the contents of the face-centered cubic unit cell is 8 corner atoms times 1/8 plus 6 face-centered atoms times 1/2 equals 4 silver atoms. Now we're given the density of silver. The density of silver is 10.50 grams per centimeter cubed, but that density is also the mass of the unit cell content divided by the volume of the unit cell. So the volume of the unit cell is the mass of the unit cell content. Well, that's the mass of 4 silver atoms. 4 times 107.87 grams per mole of silver atoms divided by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. And now we divide that by the density, 10.50 grams per centimeter cubed. The volume of the unit cell then comes out to be 6.82 times 10 to the negative 23 cubic centimeters. Not very large, but not surprising. We're talking atomic dimensions here. Well, let's now think a little further about the unit cell. Let's call the length of the edge of the unit cell L. L equals the cube root of V. And that equals 4.08 times 10 to the negative 8 centimeters. Getting down again to atomic dimensions. Now, how is L useful to us? Let's look at the place in the unit cell where atoms touch. That is right across the face diagonal. We'll call that FD. The face diagonal equals 4 silver atom radii. 1, 2, 3, 4. And the face diagonal by Pythagoras' theorem is root 2 times L. Therefore, the radius of a silver atom equals root 2 times 4.08 times 10 to the negative 8 centimeters divided by 4. And that equals 1.44 times 10 to the negative 8 centimeters. In older usage, 10 to the negative 8 centimeters used to be called an angstrom unit. And therefore, in older literature, you'll find the radius of a silver atom reported as 1.44 angstrom units. But nowadays, we prefer to use picometers. And there are 10 to the 10th picometers in a centimeter. And so the radius of a silver atom, as required in the problem, is 144 picometers. This is an illustration of how we go about calculating atomic radii from things we can measure in the laboratory. We can measure the density of silver very easily. We can determine the nature of the unit cell of silver by X-ray diffraction experiments, and so we can go directly from these data to the radius of a silver atom. And in this general way, tables of atomic radii of metallic elements have been compiled.